If you want to train a neural network to look at a picture of a face and predict someone's age, you rarely stop there. Usually, you want to extract multiple variables at once, like predicting both age and gender from that exact same image. To feed all these different input variables into a model, we arrange them into a single structured list. This array is called a feature vector. Converting data into a feature vector gives us a massive mathematical advantage. It lets us take a highly complex object, like a human face, and plot it as a single coordinate point in high-dimensional space. Look at this two-dimensional grid. Let's say we are evaluating a used car based on exactly two numerical features: the age of the car on one axis and the total miles driven on the other. That car is now a single coordinate point on this chart. By representing real-world objects as coordinate vectors, we give algorithms a way to measure exactly how similar two things are. Mathematically, the physical distance between these 2 points tells the computer how closely related those two cars are. But trying to calculate that distance using raw, unadjusted numbers introduces a major mechanical flaw. Notice the scale of this chart. A used car's age usually caps out around 10 or 15 years, but the number of miles it has been driven can easily exceed 150,000. Because the mileage values are numerically so much larger, they completely stretch out the geometry. The distance calculation is entirely dominated by the miles, rendering the car's age mathematically irrelevant. We fix this by normalizing the features before we use them. One common method is taking the value, subtracting the minimum, and dividing by the maximum minus the minimum. This compresses every feature into a tight proportional range, strictly between 0 and 1. Alternatively, you can standardize the data by subtracting the mean and dividing by the standard deviation, ensuring each feature has a mean of 0 and a unit variance. Normalization is an absolute requirement. It forces the geometry into a balanced square, guaranteeing that smaller numerical values still have an equal voice in the final calculation. That handles numbers, but cars also have non-numerical features, like color. Let's say we need to evaluate cars that are either red, blue, or white. Looking at this straight number line, it might seem logical to just assign sequential integers to these categories: 0 for red, 1 for blue, and 2 for white. Take a close look at the spacing on this axis. Why would applying this perfectly logical sequence ruin our prediction model? Algorithms read all numbers as strict spatial distances. By encoding the colors this way, we accidentally teach the computer that red is physically closer to blue than it is to white. To fix this, we use one-hot encoding. Instead of a single number, each color becomes its own distinct vector. Red becomes 1, 0, 0, blue is 0, 1, 0, and white is 0, 0, 1. Look at how these plot on a 3D grid. By assigning each category its own axes, we form a perfect equilateral triangle. Every single color is now mathematically equidistant from the others. If we fail to map independent categories into these equal dimensions, the algorithm will invent false mathematical relationships and corrupt the prediction. Now we assemble the final feature vector. We take our normalized numerical values for age and miles and combine them with our 3 one-hot encoded color dimensions. Our original 2-variable car is now represented precisely by an array of 5 elements. This logic applies to the other side of the model too. If you are solving a classification problem where the output is a distinct category, like cat or dog, those outputs are formatted using this exact same one-hot structure. When setting up predictive models, 3 rules apply. The feature space must have meaningful distances, numerical features must be normalized, and categorical features must be one-hot encoded. Proper preprocessing organizes raw human reality into a balanced mathematical space. Without it, the geometry fails, but with it, the algorithm has the precise structure it needs to actually learn.